All right, let's just jump right in. Today, we're cracking the code on a topic that trips up literally countless engineering candidates: variable frequency drives, or VFDs, and electrical harmonics. Picture this. You're sitting across from a hiring manager or maybe a senior plant engineer for that absolute dream electrical engineering role. And then they drop the dreaded harmonics question. Your palms might start sweating, but trust me, they do not have to. By the end of this explainer, you are going to be fully equipped with the perfect, structured answers to prove not just your foundational knowledge, but your practical expertise. Consider this your ultimate interview prep guide. Let's get started.
So here is our game plan for today. First, the harmonics interview. Second, defining harmonics using a really cool audio analogy. Third, decoding technical harmonic terms. Fourth, why VFDs produce harmonics. And finally, the cost and the cure.
Okay, part one, the harmonics interview, setting the stage.
I want you to step right into the shoes of the engineering candidate. You are in the hot seat. The hiring manager looks across the desk at you, and here comes the first pitch. They ask, in a standard electrical supply system, what exactly are harmonics? Now, you know that standard industrial systems typically run on a fundamental frequency of 50 Hz. That yields a pure, clean, alternating current sine wave. But how do you explain the disturbance without sounding like you're just reading a textbook? You need a clear, punchy answer that proves you grasp the physics without getting lost in the weeds. Let's build that response.
Moving right into part two, defining harmonics, the audio analogy.
First things first, you establish your baseline. You tell the interviewer, harmonics are essentially unwanted frequencies. They are extra, parasitic frequencies that sneak into the electrical system and absolutely disrupt that fundamental 50 Hz pure sine wave, causing system-wide disturbance and degrading power quality. Once you've laid down that solid technical foundation, you hit them with a relatable analogy to show true conceptual mastery. To visualize wave distortion, tell them to imagine singing a song into a pristine studio microphone. That microphone is projecting your voice out at a perfectly pure 50 Hz frequency. In a perfect setup, your voice sounds pleasant, clear, perfectly understandable. It's an uncorrupted wave. But now, imagine we suddenly introduce background noises into that exact same audio system. Say a high-pitched whine at 150 Hz and a loud buzzing hum at 350 Hz. Your original 50 Hz voice is now actively mixing with all these unwanted frequencies. The result? The audio becomes completely distorted, garbled, and honestly just awful to listen to. That audio distortion is exactly what harmonics are in the electrical world. It's unwanted noise ruining a pure power signal.
All right, part three, decoding technical harmonic terms, the math.
You answered that first question perfectly, and the interviewer is nodding along. But now, they want to test if you actually know the real-world plant jargon. The manager leans in and says, okay, great analogy, but we talk a lot about third and fifth harmonics out there on the plant floor. What do those terms actually mean practically? Do not panic here. This is simply a test to see if you understand frequency multipliers. You just calmly explained that harmonics are mathematically defined as integer multiples of the fundamental frequency. Basically, it's a direct multiplier. If your base frequency is 50 Hz, a third harmonic means you literally just multiply 50 by 3. Boom. You've got 150 Hz disturbance running through your system alongside your main power. And if they ask about the fifth harmonic, same thing. Multiply 5 by 50 Hz, which means you have a 250 Hz frequency acting as a distortion. Breaking it down this clearly shows the hiring manager you aren't just regurgitating buzzwords, you actually understand the math behind the noise.
Let's dive into part 4. Why VFDs produce harmonics, the root cause.
Okay, this is it, the make-or-break moment of the interview, the heavy-hitting technical question. They ask, why exactly does a variable frequency drive generate these harmonics in the first place? You can't just give surface-level trivia here. You have to confidently explain the internal mechanics of a VFD and exactly how power is transformed inside that drive.
So you walk them through the 3 exact steps of power conversion. First, you explain that the facility operates on a standard 3-phase AC supply. But a VFD needs a stable baseline to rebuild the frequency. So step 1, the VFD uses a rectifier bridge to convert that incoming AC into direct current, or DC, which gets smoothed out over a DC bus. But wait, the motor you're controlling needs AC power to spin, right? So step 2, you have to convert that DC energy back into AC at whatever precise frequency you want. To do this, the VFD uses an inverter section filled with fast-switching devices. Step 3, Because these devices are violently chopping the DC voltage to simulate an AC wave, they absolutely do not create a pure natural sine wave. They create a highly pulsed stair-step wave.
And here is where you drop the real knowledge. The core culprit is the sheer speed of those switching devices, specifically insulated gate bipolar transistors, or IGBTs. You tell them, these IGBTs are engaging and disengaging thousands of times per second using pulse width modulation. Because of this incredibly rapid switching, the resulting AC wave, it's not a smooth, continuous curve at all. It's essentially built out of thousands of tiny, harsh voltage pulses. Those rapid, digital-like pulses are exactly what distort the fundamental wave. That high-frequency chopping action is literally the birthplace of the harmonic noise.
Finally, Part 5. The cost and the cure. Impact and mitigation.
You've survived the deep technical theory, and trust me, they're impressed. Now we move to the final test, the real-world impact. Because a great engineer doesn't just know theory, they know how to protect the physical plant. The interviewer asks, what happens to our equipment out there if we just completely ignore these high harmonic levels? This is where you need to answer with a profound sense of urgency.
You look right at them and lay out the devastating cascade of effects. Unmanaged harmonics lead to massive system losses. Why? Because higher frequencies create the skin effect in cables, pushing current to the outer edges, increasing resistance, and generating massive heat. On top of that, these rogue frequencies cause excessive iron losses inside the magnetic cores of your motors and transformers, literally baking the equipment from the inside out. But the most dramatic damage? That happens at your capacitor banks. Capacitors naturally present a much lower impedance to higher frequencies, so they act like a sponge, just eagerly soaking up these harmonic currents. They absorb this energy, they overheat, they physically swell up, and if left unchecked, they will catastrophically burst. No joke. And to close it out, you deliver the ultimate pragmatic answer. You show them you are a seasoned pro. You say, look, the truth is, if you're using modern VFDs, you cannot completely nullify harmonics 100%. They're going to exist, but my job is to strategically implement filtering methods to control the total harmonic distortion, or THD. Depending on the severity, I'd install AC line reactors at the drive input to add impedance and slow down the harmonic rush. For bigger issues, I'd deploy passive harmonic filters to trap specific frequencies like the 5th and 7th. Or I'd even implement advanced active harmonic filters that constantly monitor the line and inject opposing currents to dynamically cancel out the noise. And my friends, that is exactly how you stick the landing.
You now have the absolute blueprint to walk into that room, break down wave distortion, and definitively prove you can protect a facility's multi-million-dollar hardware. But before we wrap up this explainer, I want to leave you with a final, provocative thought. Since we know electrical harmonics are a permanent, unavoidable byproduct of the highly efficient modern switching technologies we use every day, and they can never be entirely eliminated from the grid, how will you proactively design and manage your system's efficiency as your plant's automation grows over the next decade? Power quality is a continuously evolving puzzle, but it's a puzzle you are now exceptionally well equipped to solve. Thanks for learning with me today, and I will catch you in the next explainer.